Yeah, today we will talk about compression of neural networks. I will tell you about some recent developments, about our methods, and also some related problems. So all of you probably know that we have come to an era where we have the key ingredients to train deep networks for a variety of applications. So we have large data sets, we have computing power, and we have very elaborate deep models. And with these three ingredients, we can train AI machines which can beat human champs in difficult strategic games, which can analyze images and solve a variety of very complex tasks. However, this revolution comes at the price of complexity. So we see today that neural networks, our models, the complexity of our models is growing. We have neural networks with millions of parameters and a lot of operations which are performed for a single prediction. So we also see, especially when training these models, a large amount of energy required. So here is a study performed by researchers from MIT, where they computed the common carbon footprint for a state-of-the-art neural network, a transformer neural network with 213 million parameters, trained with neural architecture search, and they compared the carbon footprint of this single model to the carbon footprint of a US car or American average life or a round trip flight between New York and San Francisco. And you see that for training such a huge state-of-the-art model, which the carbon footprint is much larger compared to, for example, a flight from New York to San Francisco for one passenger. So we are really talking about huge computational resources needed for training these state-of-the-art models. Also, I found another example here, a self-driving car which has a lot of cameras and radar sensors, which generate around 6 gig of data every 30 seconds. So in order to analyze this data, in order to process this information, we would require big models, neural networks, which consume a lot of energy. In this case, they approximate approximately 2,500 watts of computing power just to process this information, which generates a lot. This generates a lot of wasted heat, and some prototypes even need water cooling to not overheat. So we see that the direction we are moving is we are able to solve more and more complex tasks, but for that we also require more and more energy and large models which consume a lot of power. So if we talk about processing devices at the edge, which I think is also like a key topic of the focus group AI5G, ML5G. So when you want to implement machine learning or AI on devices on the edge, in order to reduce latency, in order to reduce or to overcome bandwidth constraints, we really need to think about how to reduce the complexity of these models. Another topic which is also important here is that we recently saw a rise of a training scheme called Federated Learning, where people show that it's possible to train neural networks in a distributed fashion, so that the data, the local data, is left on the local device. So for privacy reasons, these kind of training schemes are very interesting, and especially in the era of 5G, where we can think of many interconnected devices which have local data, which sensors which collect local data. So we don't need, in future, we don't need to stream all this data to a cloud, but potentially can train our models locally. But for that we would need to also reduce the communication overhead, reduce the size of these models and the complexity. So in order to achieve, to bring these technologies to these applications, we need techniques to reduce the computational complexity. And by computational complexity, I mean computational complexity with respect to storage, but also like with respect to memory usage, with respect to energy usage, runtime, and also in federated learning application with respect to communication overhead. So of course, like having all these is very difficult and will require a lot of future research and also like a optimal co-design of techniques, training schemes, and hardware components. And but this is where we need to go. We need to reduce the complexity of these models if we want to bring them to application, if we want to bring them on the edge in a distributed manner. Yeah, and MPEG has started working on some compression techniques or on standards on compression of neural networks, specifically for the application of multimedia content description and analysis. But of course, these techniques can be applied also to other applications. So we are part, as Fraunhofer HHI, we are part of these activities together with my colleagues who have a lot of experience in video compression. I'm working on compression algorithms for neural networks. And the plan is to have the standards ready by next year. And I will tell you a bit about the current activities. And also we are very happy that our technology, which I will present you in a moment, is currently in the selected technology in the working draft. So it will be the basis of the next standard on neural network compression. Okay, so this is the outline of this talk. So before talking about DeepCABAC, I will give you some background about quantization, about encoding, about like from an information theoretical point of view. Then I will present DeepCABAC, which is a universal algorithm for neural network compression. And also talk a bit about compression aspects in federated learning. Because in federated learning, we are not necessarily compressing the models itself, but we are compressing the updates, the parameter updates which are sent around. Okay, let me start with some background on quantization and coding. So if you think about compression, so everything relates to the source coding problem. So in source coding, people kind of try to find a code, an encoder and a decoder, in order to represent a signal with a minimum number of symbols, without exceeding an acceptable level of distortion. So for example, you have some limits which are due to your channel bandwidth, and then you are trying to compress your signal as best as you can, so that it can be sent through the channel and does not lose too much information. So in source coding, you have like some source which generates your signal. So here, according to the probability distribution, here P of W. So your information is kind of W, your signal, and then there is an encoder which first quantizes your signal. And quantization is in most cases a lossy step, so you kind of lose some of the information. And then you have some lossless encoding step, in this case represented by the B, which is the binarization. And what you get is a bit stream, which you then can send over the channel. And on the decoder side, you need to kind of decode the signal. So you need to first decode the bit stream and then reconstruct the signal. And what you try is to minimize this rate distortion objective. So you want to find a code so that on average you minimize the distortion between what you send, between the W, and what you receive, between the Q, between the reconstructed quantized information. And you have some term controlling the rate, so the kind of how much information you can send around. So in this case, it is measured like as a code length. So the length of the bit stream, how many bits you need to send this compressed signal. Yeah, I mean, in general, coming up with an optimal code is very hard. It can be proven that it's in many cases NP hard, but still, like, people found ways to find some good compression schemes in audio compression and video compression. And now the task is to kind of transfer some of this knowledge, some of these techniques to compression of neural networks. So I will tell you that later what are the kind of differences between neural network compression and signal process compression, but the main ingredients are very similar. And it's for the lossless part, so we will deal a lot with the lossless coding part because it's quite important for the compression here. So it has been proven by Shannon that the minimum information required to fully represent a sample, or kind of on average, is bounded by the probability. So you kind of need minus p log 2 p bits to transfer this information on average. But in practice, often the problem is that this probability distribution is not known at the decoder side. So the decoder kind of needs to estimate this probability distribution. And even more worse, that the probability distribution may be non-stationary. So it may change over time. So, but I will show you that the technique which we are using, DeepCABAC, is kind of adapting to these changes and can deal very well with that. So what are the desired properties of a lossless coding scheme? So of course, minimum redundancy. So the code should produce binary representations of minimum redundancy. So it should be very efficient. Also, in terms of computation, it should be efficient. So the code should have high coding efficiency, meaning that encoding, decoding should have high throughput. So you don't want to wait days or hours to compress your neural network or decompress it. So you want to have some coding techniques which are very fast. And especially for the decoding, that's important. And universality, which means that the code should have a mechanism that allows it to adapt to probability model, its probability model to a wide range of different types of input distributions in a sample efficient manner, which means that you are not enforcing like a probability model on your coding, but we want a scheme which can adapt to changing probability models and also adapt when the probability of your inputs changes or is non-stationary. So these are kind of very generic properties which you want to have, which are also like well studied in source coding literature. And yeah, Cabac Cabac stands for context-based adaptive binary arithmetic coding. Is kind of one way or one coding scheme which fulfills these properties. And it has been kind of proposed in the context of video compression. So H.264, H.265, they have some kind of an entropy coding scheme based on Cabac. And so it's a well-established practical technology. And in our work, we kind of adapted it to the compression of neural networks. So we didn't like just copy and overtook it as done in video, but we kind of redesigned it and adapted it to match our needs in neural network compression. And this is a key ingredient of our compression algorithms, is context adaptive binary arithmetic coding. Yeah, so if you want to compress neural networks, things are a bit more complicated. I mean, what you want to compress is the weight matrices of neural networks. Of course, these weight matrices, they take a lot of space. So if you have like 100 millions of free parameters, weighting parameters, these weight matrices can take a lot of space, up to like half gigabyte or half a gigabyte, for example, in VGG 16 networks. And so you want to kind of find techniques in order to encode these matrices more efficiently, and also like by taking account some lossy step. But here, in contrast to signal compression or video compression, the distortion term is a bit more complicated, because what we saw here is we wanted to minimize the distortion between our signal and what we get on the other side, our quantized signal. But here we are not so much interested in measuring the distortion between the particular weight matrices, but what we want is to minimize the distortion in the behavior of the neural network. So we want the compressed neural network to have a similar prediction accuracy as the uncompressed one. So we don't care so much whether its weights are very similar, but in the end, what we want to have is similar behavior. And we know, since neural networks consist of many layers, then the errors which we make in every layer can accumulate. So the distortion matter is much more complex in this case. Also, in video, for example, or in images, you have a clear structure. So you have correlations between frames, you have correlation between neighboring pixels. So you can use a lot of techniques in video or image compression or audio compression, use this kind of structure to reduce the size of the video or the image. If you think about neural networks, there is no clear structure in the weight parameters. So many of these techniques cannot be applied out of the box. Also, in neural network compression, you have more flexibility, which means that you can not only like compress the network which as is, but you can also like fine tune it afterwards. For example, if you have some training data, you can use sparsification techniques, or even change the structure of the model. So the problem is slightly different than classical signal compression, but many of the techniques which have been proposed in signal compression can be applied. Yeah, and MPEG, the MPEG group is kind of, or has subdivided the compression problem in kind of 3 main parts. So the first part is the techniques which kind of allows some change of the structure of the neural network, like sparsification techniques or matrix decomposition techniques, which are kind of a pre-processing step to make your network, to make your model more compressible or compression friendly. Then you have like related techniques, CE2 related technologies for kind of quantization, and CE3 related techniques for entropy coding. So these are kind of the two areas where DeepCABAC is working. So quantization and entropy coding, and I will show you in a minute how it works. DeepCABAC, so it's, yeah, as I said, like finding the optimal code is in most cases NP hard, but since what you can do is you can fix this binarization map, so you can, by using a universal coding scheme, yeah, like Cabac, and then what you just need is to find a good quantizer. So you can simplify your problem by fixing the lossless parts, by using Cabac as a lossless coding scheme, and then the rate distortion problem reduces to finding a good quantizer. And if you write it like that, then you can really you can yeah, write things or approximate this term explicitly. So as I said before, in your network compression, we are not so much interested in the first place to measure the distortion between the compressed and uncompressed weights or the parameters of the neural networks, but we want to have, so that we want to find compression schemes so that the compressed networks shows similar prediction behaviors as the uncompressed one. So what we want is to measure the distortion in the outputs. So here you have like this formulation, you have like y dash and y 2 dash, and y dash is the output which you get with the original network, and y double dash is the output distribution which you get with the compressed network. So this is what you are mainly interested in. You want your compressed network to be as close as possible to the uncompressed one. So you see in this formulation that the y dash is the output computed with the original weights W, whereas y double dash is the output distribution computed with the quantized weights, with the compressed ones. Okay, so you have this, and how to compare like distributions. Usually people use KL divergence as a measure for comparing distributions, so you can do that. You can also like approximate KL divergence for neural networks, in this case using the Fisher information matrix. I will not go into details here, they don't matter. So here in this formulation you have like kind of yeah, like Q minus W, so the kind of the difference between the quantized and the unquantized weights. And you also have some matrix F, which is a Fisher information matrix. You can approximate the Fisher information matrix by using just its diagonal elements. And what we get in the end here is a formulation of our rate distortion problem as a weighted rate distortion problem. So what you see here is that you measure the distortion between your original weight Wi and the compressed weight Qi. So you want to minimize this distortion, but each such element has it's weighted with Fi, with the diagonal element of the Fisher information matrix, and this Fi tells you or measures how much this particular weight influences the output. Because in some sense you want to measure the distortion in the output prediction behavior, not in the elements itself. Okay, so this was the first version of Cabac which we proposed. So you can approximate this FIs, or you can compute them by using some Bayesian approach. And for the quantization terms, we used a uniform quantization scheme. And this were like the first experiments which we did. But later on, we found that you can simplify. So just performing a uniform quantization with the appropriate quantization bins, with the appropriate width of the quantization bins, plus Cabac performs almost equally well and is much easier to optimize. So this is what we are doing now. So we have a simple uniform quantization approach. So what we do is we have the weights of the neural networks and we apply some uniform quantization to it, and then encode the resulted, the quantized weights with Cabac. And this gives very, very good results. So we don't have all this overhead and are almost as good as with this weighted rate distortion approach. Yeah, so we have code online. So if you want to try it out, you can check it out. Okay, so it seems that most of the power of our compression algorithm lies in Cabac. So the quantization here is not such a big deal. So you can just use uniform quantization. You don't need to use this weights. So what I said before, that neural network coding is more complex because you have some nonlinear accumulation of errors. So in some sense, this does not seem to be much the case in practice. So in practice, having a good entropy coder seems to be much more important than trying to find an optimal quantization scheme. So uniform quantization works quite well out of the box. So everything kind of the magic is kind of in Cabac. And I told you before why this is the case, because Cabac is adaptive. It's context adaptive. So it can adapt to changing distributions. It can kind of automatically adapt to changes in the distribution. It has some context models for that. So I don't want to go too much into details here, but just to get you an idea how Cabac works. So you have, for example, you want to encode the number 1. So you have you weight, for example, quantized weight, which is number 1, and you want to encode it. So the first decision you need to make is like this first row, the signaling bit. So everything which is non-zero gets in 1, and everything which is 0 is 0. So 1 is non-zero, so you get in 1. Then you get the sign flag bit, which tells you everything which is positive gets a 0, everything which is negative gets a 1 bit. So since 1 is positive, you get a 1, 0. And then you have like the absolute greater 1 bits, where you make the decision if the number you want to encode is greater than 1, or its absolute value is greater than 1, then you have to put a 1 bit. Otherwise, you put a 0 bit. And in this case, 1 is not absolutely greater than 1. Therefore, you have a 0 bit in the end, and the encoding process is finished. So what you have is like your binarization of your number which you want to encode is 1, 0, 0. And this kind of binarizer is very flexible, so it can adapt almost to every distribution around 0. And the trick is that this binary terms you can very efficiently encode using arithmetic coder, which has some adaptivity component. I will not go too much into detail here because it's quite a complex topic, and it's like a well-established technology in video compression. But what we did is we adapted it to neural network compression by designing the specific schemes which you see here. So for video, these encoding schemes are kind of slightly different. Okay, so what are the results? So here we have VGG16, which has an original accuracy or top 1 error of 69 and the original size of 550 megabytes. And if you want to encode it, so we did some specification and some Cabac encoding, we could reduce its size to 8.7 megabyte without losing any accuracy. Similar for ResNet 50, we could reduce its size from 100 megabyte to 4 or almost 5 megabytes without losing accuracy. So in terms of encoding or compression strength, you see that this approach is able to reduce the size of the network quite significantly without changing its structure. This is also important because you may get similar results, maybe even better results by training smaller networks, but here we want to keep the network topology and just like yeah, more efficiently represent the network. Okay, so this was kind of the first part where we applied things to neural network compression. Now we also ask ourselves, can we use DeepCABAC, for example, for federated learning? In federated learning, you are not, what you are sending around are updates. So the federated learning schemes works as follows. So you have a server which has some initial model, and then the server sends this initial model to the clients. The clients have some local data, so they kind of train on the local data for some time. Then they are sending the updates to the server. The server is merging these different models and then sending the updated model back to the clients, and this process is repeated. So you're sending around kind of neural networks between clients and the server. And this communication is, of course, very expensive. So if you would send like the uncompressed neural networks, it would be very expensive. So people came up with a lot of different ideas of how to reduce communication load. And we also thought about using DeepCABAC as a plug-and-play compression algorithm for this case, and could see, here you can see for 3 different networks that compared to, those are training schemes, training curves. So compared to, on the x-axis, you have the bit rate, so how many bits you send around. On the y-axis, you have the accuracy. And the solid line is the original federated learning solution. And we see that, so that the dotted line is the DeepCABAC one, that we can get a significant reduction in communication by using these compression schemes. So we are compressing not the network, but the parameter update. So kind of the thing which is sent around to the server. And you can even go further than that. So you can even design specific compression schemes for federated learning, which we also did. So here is just like an example for VGG16. If you would just send the original model, you would need almost 500 terabytes to train it. So you would, because for training VGG in the setting, you need 900,000 iterations. You have like almost 140 million parameters. And if you would store every bit, every parameter with 32 bits, you get a huge amount of bits, of bytes, which you need to send around. But of course, this naive scheme would be impractical. So what people did, and also what we did, is try to come up with some compression schemes. And what you can do is you can, because the total amount of communicated bits depends on 3 factors. So on the communication rounds, how often you communicate, on the number of parameters of the model, and on the average code word length. So how many bits you need to represent the parameter update. And you can apply different techniques for reducing this total communication cost. I will just give you a very brief idea of what we did. So for example, we introduced some communication delay. So we didn't communicate every time the clients have a new data point, but had some communication delay, which allowed us to compress or reduce communication by a factor of 100 to 1,000. We also didn't, of course, didn't send the full weight vector, but the updates, and also specified the updates and even binarized them. So in one communication round, we sent either 0 or the positive value. And in the other round, we set either 0 or the negative values, and also used some optimal schemes for encoding these positions. So when you have like the parameter vector which you want to send to the server, you specify it, so you have a lot of zeros, and some of the entries are non-zero. So you want to optimally encode these entries, and we use column encoding for that, and propose also to use some local error accumulation. And this works very well. So here you see some results. So the solid line is the base, the blue line is the baseline. The blue solid line, this is how it would look like if you would send everything. So you see that you would need the 10 to the power of 15 bits. It's too much. And the blue dotted line is a federated averaging solution, which was proposed by Google some time ago. And our lines, the green ones, are the sparse binary compression solutions. So we even get a reduction in communication overhead by almost 2 orders of magnitude compared to federated averaging, which is without a loss in accuracy. So we still get the same error performance in the end, but have to communicate much less. So yeah, so for example, from 125 terabyte to 3 gigabyte, which makes a huge difference in communications applications. Yeah, you get similar results for other data sets. So it's not only for this one particular network and data set, but it's also for other ones. And currently also MPEG is thinking about having like a standard also for this incremental learning scenarios where we send around updates or incremental updates to a model. And so there is a call for incremental neural network and in our test materials, and we will participate in this as well. So we will adapt our DeepCABAC solution to also be applicable to this federated learning or incremental learning scenario. Yeah, that's it. So you see that efficiency in storage, memory, energy, runtime, communication overhead is very important. It's very difficult to solve all of it. I mean, I just presented like a solution for the storage and communication overhead aspects. Yeah, DeepCABAC is based on established compression technology from video compression for the video coding standards. It's adapted, so it's really adapted to neural network setting. And in neural network compression, you have more options. You can fine tune. You can people are using neural architecture search. So there are a lot of other things you could do in addition to compression. And also in practice, hardware co-design is crucial. So we are currently also working on some specific hardware implementations of these compression schemes. And yeah, the MPEG standardization is moving forward, and I'm very happy to be part of it, and also happy to get to have the support of my colleagues, and together we are very happy to be so successful in that. So we have a couple of references, a couple of papers if you're interested on federated learning, neural network compression. I also prepared, or still in the process of preparing, a website, federated-ml.org, where I also put some of these slides and the papers and our recent developments code. So if you're interested in seeing what's going on in these areas, you can check out the website. And thank you very much. I'm happy to answer questions. Thank you.
Thank you so much, Wojciech, for going through all the slides and presenting to us a universal compression for deep neural networks. Now we are going into the Q&A session. So my colleague Vishnu is going to moderate. So Vishnu, welcome and good evening.
Thank you, Thomas. And as usual, it is a pleasure talking to Wojciech. Wojciech, I think it's a very interesting presentation. In fact, I still have my notes from your presentation in our Berlin workshop for the focus group. And I was comparing as you speak. You seems to have made a lot of progress after that. So thank you so much for updating. And my first question is about interpretability. So I know your interest in this topic. You know we have discussed this before.
Yeah.
You in about slide 19. I think you talked about the Fisher information metric,
yeah.
And you mentioned about finding how much the weights influences the output. I think that's what you mentioned.
Yeah.
So this actually is the definition of interpretability, if some way you look at it that way. So I want to ask you, what is the relationship, and whether you have what are your thoughts in general? I'm sure you have some very interesting thoughts which I would like to our participants would like to hear.
Yeah, I think that's a really great question. Thank you. Yes, there is some very interesting work by Max Welling and colleagues about Bayesian neural network or Bayesian compression of neural networks, where they kind of establish this relation. So I think from a theoretical point of view, I think this is kind of the right way to go, because you, as I said, I mean, in the end, we are not so much, we want to measure the distortion with respect to the prediction behavior, not with respect to the particular weights. So I think this weighted rate distortion formulation of the compression problem is, from a theoretical point of view, the right approach, and there is like this Bayesian work which kind of supports this. But like from a practitioner's point of view, I think it has some disadvantages. As I said, here we kind of moved very quickly to leave out this term because in terms of performance, there was not so much difference in terms of compression performance. So it seems that the Cabac component is much more important and influential for the compression strength than measuring the clear relation between how much this weight affects the outputs. And as I said, if you're looking for code, so one desired property is high efficiency. So you want your compression coding and encoding schemes to be high throughput and fast. And if you would take it from this Bayesian point of view, you would be very limited, because, for example, having like this estimations for really large models is very, very time consuming. And therefore, from a practical point of view, I would not recommend this, but from a theory perspective, and from an interpretability perspective, I think they have a lot of value.
Thank you so much, Wojciech. That makes sense. I want to ask you about this distribution of data. So you talked about distribution of it being you were talking about. So how do you relate this to the type of data? because when you compare data sets versus what we face in the networks, there is a huge variation in the type. How do you see this adapting with respect to the data, the variance in data that we are getting? Would this kind of a solution be able to handle the network data that we see in communication networks, 4G, 5G type networks?
I think so, because I mean, this adaptation is also like of crucial importance in video, right? If you're encoding videos, things also need to adapt very quickly, because once a new frame comes in, the scene can look like very different. So you need your coding scheme to very quickly also adapt its probability estimates and it's kind of how it looks at the data to these new situations. So I think this is one of the big strengths of Cabac and DeepCABAC, that it can very efficiently adapt to changing distributions. And I would think that I mean, of course, it depends on what is the scale, the time scale of the changes. If the data changes like every millisecond, maybe you will not be able to adapt to it due to practical reasons. But in principle, I think from a methods perspective, these techniques are adaptive, and I think this is one of the main strengths of these technologies, not only in neural network compression, but also in other applications such as video coding or other signal coding applications.
Thank you, Wojciech. I want to go to slide 26. I think there was something really interesting there. This is, in my opinion, the crux of mapping between the multimedia compression techniques and the neural network compression techniques. So I want to ask you, you talked about something really interesting here, and my note says that you were adapting the scheme from this domain of multimedia compression to neural network compression. I want to ask you, what are the factors that you kept in mind? Of course, you talked about the distortion, but apart from that, while designing this sort of a scheme, I mean, this looks like, to me, it looks like a really thought out scheme, and it looks well thought out. So I want to ask you, what were the factors which went into designing such a scheme?
Yeah. So we have a colleague here at front of HHI who has like a lot of experience with Cabac and has been working for this video Cabac implementations, and we were very lucky to have him as part of our new team on neural network compression. And he actually, what he did is he kind of looked at the empirical distribution of compressed neural network weights. So what we did some experiments, we did some preliminary experiments and just checked the distribution, how are things distributed. And then he came up with this scheme to, for example, we saw that the distribution was mainly around 0, but it was skewed. So it was not like a Gaussian distribution, it was a skewed distribution. So he came up with kind of, this kind of scheme to capture the shape of these distributions as best as possible, or at least from this empirical experiment. So it was a really iterative process where we came up with this new decision schemes and also like checked how things are distributed in the network. And it's possible that maybe at some point someone else comes even with a better scheme, which is even better for neural networks. So this is, I think, an empirical process, learning by doing. But this colleague has, I think, a lot of experience in this thing. And he said that, he took a lot of effort to coming up with this kind of scheme. So at least for these experiments which we did in MPEG, we are also not working on 1 or 2 networks, but there are plenty of different models also in different domains, not only images. And this Cabac approach works quite well for this variety of models. So I think it's quite universal in this sense.
But just one more question, maybe Wojciech to ask. There is maybe one of the participants here is having a more or less like an introductory question that asks if maybe if someone is new to artificial intelligence or to this kind of area of neural networks, what kind of resources or how they can go about it?
I mean, luckily the entry barrier nowadays is not that high. I mean, there are a lot of good libraries from Google, from Facebook, like PyTorch, TensorFlow, and all these kind of libraries which you can use to play around with neural networks, with AI on your local computer. So I think for just playing around with some toy data sets or with some like standard networks, the entry barriers are very low. But when it comes to like really practical issues and implementing things in practice, and reducing energy, reducing the size of the reducing communication overhead, then I think things become very tricky, and as some of these things are still in the research. So I think we will see in the next years how standards in this area will be accepted by industry, and I think this will also need some time to see how these things are accepted.
Yeah, I have put the papers from Wojciech actually, which he had distributed earlier. So these are good starting points as well. I think there are many references in there as well, which Wojciech's paper has. So once again, thank you so much, Wojciech, for taking these questions very patiently and explaining these concepts. Maybe one last question. Could you talk about your future research? Where do you go from here?
So I'm now very interested in federated learning, and I think I mean neural network compression and also like efficient inference. It has a deep connection to hardware co-design, and I'm not so much experienced in hardware. But what I think is that in machine learning, these federated learning schemes, distributed learning schemes, they are very, from an algorithmic point of view, they are very interesting. And yeah, we are working on different extensions to current schemes. For example, usually people used, or federated learning, it was assumed that all clients have the same model architecture. But I think now people started to propose techniques where you can train also like different models with different architecture on each client, which I think is also a very interesting topic from an algorithmic or the theoretic perspective. So I want to go deeper into federated learning. I'm now in the process to edit a book also on federated learning with some colleagues. And yeah, I'm looking forward to see how this field will develop. And of course, I'm still interested in explainability, explainable AI. There are also like a lot of very interesting developments going on. And also like, I mean, with my colleague, I will still be part of this MPEG standardization. So I'm also looking forward to see how these things which we standardize will be implemented by industry, how they will be accepted. So I think this is also very important to see and also like to maybe improve the standards over time.
Interesting. So yeah, we look forward to reading your book as well as your standards on the MPEG side as well. One question from the audience about the relationship with the hardware co-design. I think the question is especially because of federated machine learning and perhaps the use of accelerators and other types of processes in the distributed environment which you talked about. So how do you connect these two?
Yes, I think, I mean, you have to distinguish between, I think, inference and training. I think for inference, I think like nowadays we are moving very well to bring AI on the edge, and we have like this very good accelerators which allow to execute models, yeah, with much less energy and other requirements than before. I think for training, it's still difficult to train like large scale big models in distributed fashion, simply for this complexity reasons. So, but I'm tracking the development in this hardware or accelerator field, and I think people are also like moving very fast in this research area. So that's good to see, and I hope that yeah, that in the end we will be able to train and execute big models in a distributed manner without much energy requirements.
Thanks, Wojciech. It is always a pleasure talking to you. I hope to read your publications in future. And once again, thank you so much for answering the questions.